Okay, thank you again for attending this lecture. So yesterday we have seen some trailers about conspiracy principle and catastrophe principle. So there's a sharp dichotomy between heavy-tailed and light-tailed rare events, the way the rare events arise. So those dichotomy can be characterized precisely from large deviations, in particular sample path large deviations. So let me start with briefly reviewing the light-tailed large deviations theory. So can I ask who's not familiar with light-tailed theory? Okay. But let me still briefly recall the light-tailed large deviation. So the large deviations principle is an established terminology that describes asymptotics of this form. So we say that Sn had a sequence of random variables. So this can be real valued random variables, but this also can be some arbitrary, so it can be, for example, cat or function valued random variable or any random object in topological space. So Sn hat satisfies LDP with a ray function I if the probability that S hat n is in set A decays at exponential rates that are characterized by I. So a few clarifications. So here, this is the interior of A, and this is closer of A. Closer. Can you all see? Okay, yes, closer.
I'm interested. Why do you need hat for Sn?
Sorry.
Why do you need hat here? Do you use Sn without hat?
Yeah, it's just name. So
It's raining here.
It can be Xn, it can be Sn. So it's not necessary. I just picked S hat n because I'm going to use S hat later. So yeah, I will have some specific choice of S hat n later. All right, so this is the obviously this is large deviations principle, and so yeah, so these are closer and interior of a set A. So if you take infimum over some set, this is a smaller set than this set. So the infimum will be larger here. Infimum will be smaller, but we're taking negative of that. So this is smaller than this one. Okay. So lower in upper bounds. They are tight if the infimum over closer and interior coincide. And so because of this, the large deviations principle is inherently topological. In other words, if you have binary topology or binary topology, then the closer will be closer to the original set. Interior will also be closer, it is smaller than the original set, but closer to the original set. So finer topology, you're gonna get more interior, more closer. That means closer approximation of the original set. That means these two will be closer to each other. So you get tighter bound. So there is always this trade-off when it comes to the large deviation principle. If you can establish LDP for finer topology, then you get more useful bounds. But it's harder to establish. So you do more work, and people use your work will be will have easier time. If you pick coarser topology, then your bound is not as useful, but it's easier. So your job becomes easier. Sometimes LDP simply doesn't hold for fine topology. So we're going to get back to that later. But the point I'd like to make here is that the topology matters here. Okay, so the rate function, the definition of rate function is that the sub-level set is closed for all alpha non-negative, and I is a function from the space X to non-negative real numbers. So I here more or less encodes the rarity. If I is large, that means that the point associated with that is more rare. And so being closed, so this condition that I that controls this LDP is a rate function. So it's this condition is lower semi-continuity, and this is important because there are some very useful properties, implications of these depend on the eigenrate function, and in fact, you say that it's good.
Zero to two. No, it is absolutely different. Distance to.
If the lower sub-level sets are compact. So let me quickly point out that what lower semi-continuity or being a rate function means. So if your function looks like this, and here you can go down, you can jump down, then this is still a rate function, because if you take the sub-level set here, then this is a sub-level set and it's closed. But if the continuity is in this way, then if you take the sub-level set, let's say here, then the sub-level set becomes this set, which is not closed. So this is not lower semi-continuous. So what it means that the continuity can only be jump down. All right. So what's useful about this formulation? This formulation is that if you have good rate function and your random sequence of random variables satisfy LDP, then the continuous image of that also satisfies LDP. The new rate function, though, is in this form. So the infimum of the rate functions, the original rate functions, for x, that gives you y. So it's inverse. X is the inverse image of y, and you're taking infimum over the inverse image of y. So again, the smallest value of the rate function. So that means most likely value, right? Because a large rate function means less likely or more rare. So small value of rate function means most likely, more likely. And we're taking infimum, so it's most likely point of the eyeliner is not shown very clearly, but I guess you can still see it. Anyway, all right, so that's called a contraction principle, and this is basically a continuous mapping principle, but somehow in LDP literature, it's called contraction principle. And so why is this useful? Once you establish LDP for Yn, then you can study many different aspects, and you get LDP for many different aspects of Yn. So some by taking a function of y means you're focusing on some aspect of y. So we will see more examples later, but this is why one of the reasons why you want to have LDP is once you establish LDP for the system, then you can answer lots of questions about some components. So the first large deviations principle was probably Kramer's theorem. And the statement is simple. You have IID samples, real valued, mean mu, and take the sample mean. Then the sample mean satisfies large deviation principle. And the rate function here is the Fenchel-Legendre transformation of the log moment generating function. So, and I suppose that you are all quite familiar with this. Again, the form becomes this. And because it's just about the sample mean alone, by the way, this formulation can be interpreted in this way. So probability of x hat in A number decays at a rate, so e to the negative n. This, especially if the lower and upper bounds coincide. So basically, this is the exponential rate. So this part is an exponential rate, and this tells you the exponential decay. So I put a dot here because it's not the same as the asymptotic equivalence Jorge used yesterday. And what this means is that it's same at an exponential rate, but there can be some slower function sitting in front of this. So there can be some polynomial rate here. We are here in this log asymptotics, we are ignoring those as slower than exponential. Okay, so this is likelihood large deviation, and you see that here this phi is infinity if x is heavy tails. So the definition of heavy tails is not exactly, I didn't give you the exact definition, but if you don't have exponential moment, that's what That's what I am usually inclined to. If you don't have any exponential moment, so this is equal to 1 if lambda is 0, but other than 0, suppose that it's always infinity. Then this thing, whole thing is negative infinity except for the case where lambda is equal to 0. So, and when lambda is equal to 0, these are both 0 because log of 1 is 0. So this is 0 when and this is 0. So that means here it's 0. So what does this mean? The rate of decay is slower than exponential, but you don't get any more than that. So Cramer's theorem still applies, but in heavy tail cases, you can actually do much better. So the classical heavy-tailed large deviations result is negative theorem. So same setup, IID, mean mu, and take the sample mean. And here we assume that xi's are heavy-tailed. So there are many different subclasses of heavy-tails. So here it's sub-exponential. This is probably one of the most general definition of heavy-tails. And this includes all the important heavy-tail distributions like Pareto, log normal, and Weibull, which are considered the trinity of heavy-tails. And this probability, the sample mean being above mu by epsilon, decays at this rate. So has is you divide that by this, then it converges to 1. So this and this are asymptotically the same in the sense that Jorge used yesterday. So so you see that this is exact asymptotics. It converges to 1. It's not. There's no ambiguity about it. So it's not log asymptotics. It's very exact asymptotics. So in other words, you can do so this can be some polynomial rate, or it can be the tails of the log normal or Weibull. But you have very exact asymptotics. All right, so there's this. So there are, like, we can discuss more about how to interpret this in the so-called principle single big jump. But let me not do that because the catastrophe principle is more general a statement, and we're gonna get there. So this is these are the simplest form of large deviations in light-tailed and heavy-tailed context. Now, why this large deviations principle is so useful becomes much more obvious when we start to look at the sample pattern. So let's again call the sample mean x hat n, and we consider scaled version of it and embed it in the continuous space. So here, this is this looks like this. So it's this value. Here. And this one is continuous interpolation of those. So you have This. Well, if you look at this one lives in the space of continuous functions. And it turns out that large deviation principle holds for the path of S hat n. So you consider S hat n as a random function or element of this continuous function. So that this is a C01 valued random variable. And so those random variables satisfy LDP with the rate function in this form. So again, lambda is a log moment generating function, and lambda star is a convex conjugate, and the rate function has its derivative evaluated at the convex conjugate lambda star and the integral of it. So the value of rate function is finite in this value if f is absolutely continuous and starts from 0. Otherwise, it's infinity. So remember that in the previous, yesterday's lecture, that the heavy-tailed limits had discontinued. So you cannot characterize the likelihood this way. So indeed, the Mogorsky's theorem has this condition. So you need to have finite moment generating function everywhere. So okay, so let me finish the discussion of the light-tailed LDP with what makes it so useful. So the rare event occurs in the most likely way. So we have already seen. So let me. So this was the simulation result from so this was the simulation result with of the rare events that the path hits below 0, and in the light tail cases, it was always because of this particular scenario. So remember that this happens because of the randomness. If your system was, let's say, if xi's independent increments are actually deterministic, then it's going to be just straight line. It's not going to deviate from that. And it deviates from that and becomes like this, only because of the randomness. But whenever this rare event happens, it happens in a deterministic way. Almost deterministic way. So this makes the identification of the most likely reason, in particular as the infimum of the rate function here, so useful, because that infimum is exactly how this rare event happens. If you want to prevent it, somehow you can do about that particular scenario. All right, so this theorem tells you that tells you that rare event happens in the most likely way. And the statement of theorem goes this way. So suppose that C is a closed set, and if you take the infimum over that C, then because of the rate function, if I is a rate function, then you know that the infimum is attained. But let's suppose that the infimum is even attained within in the interior of C. And let's say that value was K. Then and you consider the neighborhood of the set of values that gives you K. And then the probability that Xn is outside of that neighborhood, given conditional on the rare event, goes to 0. So this means that it happens because of exactly these scenarios. Is this correct?
Could you repeat the take-home message again?
Oh, so this set B is something that's just slightly larger than the scenarios that contain the most likely scenarios, right? So the infimum of this, so remember that I encodes the rarity. So small I means more likely. So infimum of I is the most likely one within C. So that value was K. This set is the scenarios that correspond to that value C. So these are the most likely scenarios. Now, you take the neighborhood of that, just slightly larger than that. And you always have to be within that. Like the probability that you're outside of that goes to 0. Conditional on the rare event. So when the rare event happens, it's almost always because of the scenarios that are the most likely scenario in C. Does this make sense? Yeah. So okay, repeat one more time. So infimum is the x's that attains the infimum are the most likely scenarios. So this is a set of most likely scenarios. You make it slightly larger, then you cannot be outside of it. You have to be inside of those somewhere close to the most likely reasons. So here,
So C is the rare event, and then
right? See, exactly.
and then the smallest x given K is the most likely explanation.
Right, it's most likely scenario. Yeah. So if you go back to these, so these are the straight line is the precise straight line is the most likely reason. This is remember the variational problem in Mobius theorem that we solve. So okay. So I is in this form. So you're taking infimum over all possible paths. And the value that you take infimum has to do with the integral of the derivative. So it's variational problem. So if you solve this problem, what you're gonna get is this straight line. And that's the x that attains the infimum. If you make it slightly larger, so you consider cube around this, probability that conditional probability that the scenario deviates from this cube goes to 0, conditional on this variable, the bankruptcy.
So this straight line is from the starting point to the time horizon. Yes, it's one.
Yes, starting point to the end of the time horizon.
Yes.
Yeah. All right. Okay, so I hope this is a little bit more clear. All right. So
So C is the bankruptcy event in this case.
right. Right. So, for those of you who were probably not here yesterday, let me remind you a little bit. So, this is the classical insurance risk model, and so I am scaling it both linearly in time and space, and these are simulation results, the 10 simulation outcomes, and as n increases, some pattern starts to arise, and this is dictated by the law of large numbers. So the path is supposed to converge to this straight line, and if you consider, so and this was regardless of the tail distribution, both heavy tail and light tail distribution, same pattern. But in if you consider the rare events, then in particular this rare event, so the event that the capital reserve goes below zero, so you can think of this as bankruptcy. So these are possibilities, but in heavy tail and light tail cases, different patterns arise. So again, this is the same experiment, except that I discarded all the non-bankruptcy scenarios. So I only collected bankruptcy scenarios, so that you can interpret this as a sampling from the conditional distribution on the bankruptcy. So as the scaling parameter increases, you start to see some pattern rising. And so in light tail cases, these are the patterns, and in heavy tail cases, these are the patterns. So we'll get there later, but yeah. So this light tail case is a manifestation of the theorem that I've just showed you. So here, C is the bankruptcy scenario.
So C is B in this case, right?
Yes, exactly. Sorry. And then yeah, so these wiggles are within the neighborhood of it. All right. So this is why large deviations theory is so useful, because it precisely characterizes how the rare events arise. Okay, so let's move on to the heavy tail counterpart. So for a long time, there was no heavy tail counterpart. And by the way, again, this is awesome because you have sample path large deviations. So it's, you're looking at the whole system, the whole history of the system. So because of this, you can precisely characterize how exactly it happens. Like it starts from here and linearly goes out and hits zero at the end of the memorized. And if you only had the LDP for the endpoint, then you can tell that it happens because at the end of at the end of time horizon, you exactly hit zero, but you don't know what happens in the middle. And you know all of this because you have sample path large deviation. So in light tail context, light tail literature, there is beautiful theory that you can first establish a finite dimensional LDP and then lift it to the infinite dimensional sample space. Those machineries actually break down if you have to deal with heavy tail cases. And that's why you have this condition in both that you have all exponential moments. So in the heavy tail literature, there have been this folklore called principle of single victim. And in other words, the rare events, system-wide rare events happen because of the single big catastrophic failure of single component. And in fact, Gana, along with Henry Colt, Philip Linscott, and Thomas Mikosh, has came up with fantastic functional version of negative theorem, basically, around 2005. And I think that was Bert's inspiration. So there's this fantastic counterpart in light-tailed world, but in heavy-tailed world, the approach has been more ad hoc. You solve in the particular system case by case. So that functional version of large deviations was very full development. It was limited to the single catastrophe, single principle of single big jump. And Bert, Dima, and Sergey, they all knew that it's not always because of single big jump. So Bert wanted to do some have the same systematic approach as the light tail case, and wanted to come up with sample path version of large deviations in heavy tail companies. So that's when I joined CWI as postdoc, and Bert and I started working on sample path version of fully general sample path version for heavy tail large deviations. All right, so so this is the result that came out. The first result that came out from that direction of research. So again, suppose that we have regularly varying increments, and so here I am mixing up locations. So the path of random walk satisfies this version of large deviations. And again, what's really wonderful about the sample path large deviation here is that the statement of the large deviations is that A is for any measurable set A. So these bound should hold for any A, and if it's in sample path large deviations, this is the path space. So in case of the Mogul-Skip theorem, it was continuous functions between 0 and 1. And any set that describes the path can be here. So you can ask lots of like these variables of these types. It's broad, very, very broad class of variables. So for some general set A, we can have similar upper and lower bounds. And here, though, we don't have log here. So it's again precise asymptotics, just like negative theorem. And the lower and upper bounds have to do with interior and the closure. So again, this is very topological. And the choice of the topology matters. And this is the rate, the number that decides the rate of decay, how fast this rare event becomes rare. So yeah, this is a regular LDP. This is heavy-tailed large deviations.
Can you remind us what the notation for the A's is? So this is the interior of the set and the other is
Right, this is interior, this is closure.
What is the notation denominator? I'm a bit confused.
Denominator, oh, okay, so all right, sorry about this. So here I have a typo because thank you for asking. Yeah, so the tail of the increments. And the reason I have typo is because when I go into the details, I'm gonna actually look about Levy processes. All right. So this is how the heavy tail theorem looks like. But what do I mean by general? So let me make it very precise. Okay, so we should oh, by the way, again, this is topological, so I need to actually specify which topology I'm talking about. So we are going to consider path space, especially RCLL space or cat-like space. So right continuous with left limit. So yeah, I guess you all are familiar. And the metric there, so there are a few different popular metrics defined on the score space or cat-like space. And this is probably the most popular and probably the most useful one, J1 topology. So this is the identity function. And these are the supremum norm. In other words, this is the supremum f between 0. And this is the set of all non-decreasing homeomorphism between 0 and 1. So what this means is that you can so here lambda, you can think of it as a deformed time. You distort time a little bit, and so one of the paths you distort time, the other one you keep the same, and you can make it as close as possible. But you cannot deform the time too much, because then this will be large. So you want to keep both the deformation and the distance after deformation small. So what this allows is to consider, for example, so this is one path, let's say, one function, and this is another function. Then is this the distance or is this the distance? So if you take the supremum norm, then the distance is this much, right? But if you allow time deformation, distance becomes more or less like this. So what J1 topology, J1 metric allows is to consider similarity like this. Okay. So in this sense, it's not as fine as the supremum norm. So some things that are close in this J1 sense may be actually far from each other in supremum distance. But you will see that in heavy tail cases, supremum norm is not very useful because you see that there were jumps. You want to consider these things close. All right, so now we're going to define d sub I as the paths that start from 0, non-decreasing, and they're step functions. So it's continuous, constant almost everywhere. And there are exactly I jumps. So this is this, we first let me make it relative. So this is the number of upward jumps in the path sheet side. If there's a grid, I apologize. But I'm gonna call it side. Okay. So all right. So these are the step functions with exactly I jumps, and they're upward. These are the set of step functions less than j jumps. These are the step functions with less than or equal to j jumps. So pretty self-explanatory. And this is a set of all step functions, non-increasing step functions. So it doesn't matter how many jumps, but it can be, you can have up to countable jumps. Okay. Now, so we're gonna do the LDP for the Levy process because the way we obtain LDP for the random walks was first establish LDP for Levy process and then obtain LDP for the Levy process from that. Okay, so Levy process can be always decomposed in this way. Levy-Ito decomposition. So linear drift. This is Brownian motion. And then this represents small jumps, potentially infinite number of jumps. These are the jumps that are larger than 1. So this part is more or less Poisson, compound Poisson process. So these are Poisson random measure. With Poisson random measure with mean Lebesgue measure product Levy measure of the original process X. So don't worry if you feel rusty about this, but the point is that this is a drift, and there's some drift associated with it. So these are those drifts, and what we're going to consider is basically scaled both in time and space version. So centered and scaled version. Here, nu gamma is a measure of this form. So this is basically power law. And J-fold product restrict on this set. So what is this? This is the ordered set. So the first coordinate is larger than the second coordinate, and so the coordinate wise is decreasing. So that's restriction on that part of the space, of the J-fold product measure. And C of J, so remember that C of J was the lower, it's a measure that appeared in the lower and upper bound of the large deviations. Is in this form. So it's the measure of the sets for which this belongs to. So this is it's going to be evaluated at events or sets in the path space. So there will be a set in the path space. So this is a path, right? So at UI, you make a jump. The size is yi. So this is a step function with exactly j jumps. Right? So C is a measure that has this much. So here yi's are associated with this power law. So they are more or less they more or less follow the power law with index gamma, and UIs are IID uniform. Between 0 and 1. So jump times are IID uniform. Jump sizes are follow the power law. And so this is a measure defined on the paths. So supported on the path with exactly j jumps. And the size and times of the jumps are more or less power law and uniform.
And the expectations taken over UIs?
Right, yeah, exactly. Yeah. All right, so now let's remember that J of A was the smallest number of jumps required.
Decreasing.
So this was the quantity that played the same role as the rate function in the Light-Tailed function. And J of A can be defined in this way. So remember that this was the number of discontinuities. And this was the set of step functions. So you take the elements of A that are step functions, non-decreasing step functions, and take the infimum among those of the number of jumps. So this is exactly the number of jumps for a step function to have to enter set A. Right? Okay, let me just repeat. This is the set of paths in A that are step functions. Okay, step functions in A. This is the number of jumps. We're taking the infimum, so the smallest number of jumps in set A for step functions. Okay.
This restriction.
It should be minimum, not infinitum.
Right. So yes, because it's discrete. In the end, it is minimal. Yes. Yeah.
I'm a little bit confused. So this mu gamma j
Mhm.
is a measure which lives on this simplex.
Right. In RJ. Yes.
But then you apply to a set where these y's
yeah,
are
so-
not in the simplex.
Sure. So so this what is this set? This is a set of J tuples for which this belongs this. Let's say so. Let's just make the set. Let's call this set A. Evaluated at A. So A is a subset of paths, subset of score space. And each of these are paths. So if you fix, so expectation will be taken over use. So let's first assume that you are given. Okay, so you fix uniform random variables, realization of the uniform variables. Once you fix U, and depending on what y you choose, the path is decided. Right? Once this path is decided, you know whether it belongs to A or not. So you collect all y's for which this path belongs to A. So that is the set that you evaluate nu alpha j at.
That set will necessarily be in this decreasing order, this wise.
Right. So if it doesn't belong to this set, then it's zero. Yeah. So the part that it doesn't belong to that, it's just zero. So you can also just think of R plus J now. So it's also
Because I was
you can-
confused by the word restriction because I thought
Ah,
that measure
I see.
was just there.
right.
But in fact, you want the whole measure, you just want to take the times the indicator of that set.
Right. So it's yeah. So you can just think of the extension of that and just
Yes.
put measure zero outside of it.
Yes.
So do you really need to order the sizes of the jumps? What's going wrong if you don't order them?
If you don't order them, you can just divide by n factorial, but nothing.
It's just a symmetry.
Right. Okay. Yeah. So
Chamber.
right. Yeah. All right. So J of A is the smallest number of jumps required for a step function to be inside the set A. All right. So the main result, the first main result, is this. Suppose that A is bounded away from E less than J of A. Remember that E less than J of A was the set of step functions, non-decreasing step functions, with less than J of A jumps. Okay. So set A is bounded away from D of J of A. Then this asymptotic form. So again, C of J is this C of J. J replaced with J of A. This number. And closer interior and limits are bounded by these. And the normalizing sequence is this. So remember that nu was a Levy measure. And
Sorry. So we don't need the nu to be the stable measure, right? So
no. So that's like this is so it doesn't have to be so you can have like 5 moments or 100 moments, million moments. Only what all you need is regular variation. Okay, so
And bounded away in the Skorhot topology, right?
exactly, yeah, J1. Yes. So one thing. So let's suppose that you're interested in this set A. So this set is the paths that whose supremum is greater than 5, but the jump sizes cannot exceed 2. So paths like this, but so J of A is clearly 3, right? So 1 jump, 2 jump, not enough, but 3 jumps, enough. But how are you gonna prove? Like, is it for checking that A is bounded away from this set? It's doable. It's not that difficult in this particular case, but you can make it a little bit easier. So this condition actually can be relaxed to this. So yeah, you don't have to check. Okay. Thanks. So you don't have to check all the paths in A. You only have to check the bounded awareness of the step functions in A. Okay. It's different. The distance between sets in A and the functions in step functions in this set, or the distance between all the step functions in A and the step functions in this set. They're different, right? And you're only considering the distance between the step functions, so it's easier to verify. So this is a small point that you can actually only it's enough to verify this instead of bounded awareness. Okay. All right. So in this case, J of A is equal to 3 because you need at least one jump, two jump, three jumps, and that's enough. All right. So this is a large deviations, heavy-tailed version of large deviations. Do we also have a similar result as what I've shown about the most likely path? So we actually have even more, sharper result. In other words, if under this condition, so the lower and upper bounds coincide, the conditional distribution, given that xn belongs to set B, the distribution of the random variable, distribution of the random path converges to some limit random variable. And this measure is actually exactly in this form. So this is convergence in weak convergence of the measure. And remember that this measure was supported on the jumps with exactly JB, exactly with JB jumps, like step functions with exactly JB jumps. So, and what this means is that you're here you're taking the intersection with B, and we're assuming that JB is bounded away from B less than JB. So what this means that the JB jump is bounded from below. So this random object is step function with exactly J of B jumps bounded from below. So remember that we are looking at a scaled process. So bounded from below means a scale of order of n. So this exactly characterizes there will be order n exactly J of B order n jumps. So now going back to this thing. So here it's okay. So here, so this is not exactly a mean zero function, but it's easy to actually translate this to process it with drift. So you see that here it's all straight line plus one jump, single jump. Okay. And one thing to notice here is that in the light tail case, it was deterministic path, just single deterministic path. Here, it has very special structure, very specific structure, but the arrival of the jump, arrival time of the jump, is random. So we do have we know that it happens because the most likely reason, but the most likely reason is not deterministic; it's random, and that randomness is precisely described in this way. All right, so that's that's the capitated large deviations. Let me say a little bit about how you can prove this. So again, Levy-Ito decomposition. You have Brownian part, the small jumps, large jumps, and some centering. So it turns out that this part is to this, and which is in turn close to this. This. So what do I mean by close? I'm going to make it clear, but just intuitively, they are close. So here mu1 plus is the conditional distribution of the conditional expectation of the jump, large jumps. So given that, so conditional expectation of the jump sizes, given that it's greater than 1. And what this tells you is that they are just, you can just ignore this more or less, because these will be large. What are these? So here, Q and inverse is just inverse of the pseudo inverse of Qn, where Qn is this tail function, tail distribution function of the Levy measure multiplied by n. What's gamma? Gamma is the just gamma distribution. So sum of exponentials, IID exponentials, standard. So jump sizes are something that you have very particular representation. Jump times uniform. So let's see. So what I mean here, close, is what we call the asymptotic equivalence, which is not the same as the ratio going to 1. And I'm going to give exact definition soon. But basically, if you have asymptotic equivalence, then it means that they satisfy the same RT. So the way we proved this was this has the same, this satisfies the same LDP as this one, which satisfies the same LDP as this one. And these, again, this one and this one satisfy the same LDP. So the key mathematical machinery that we found really useful was which is generalization of the notion of regular variation to the metric space. But it's also we also found it really useful for like this purpose. So so suppose that S and D are so S is a complete separable space, a metric space with respect to the metric group, and C is any given closed set, let's say closed cone, and we define the space of measures, space of Borel measures, MSC as the ones that have finite measure, if you take them outside of C. So here the definition is the fattening. Here it's R fattening of set C. So all the points that are within R distance from C. So if this is C, then this is R fattening, C R. And here it's open fattening. And then if this is the entire space S, then we're looking at this portion of S. So if mu assigns finite measure on this kind of sets for any R, any strictly positive R, then that measure belongs to this set.
Should C be a count?
So so it does not necessarily have to be cone, but it's convenient in certain for certain in certain contexts. So in this definition, you don't need cone, but we're going to work with cones like the D's that we are so those. Okay, so the convergence in this space is defined in this way. So we say that mu n converges mu in this space if the lim sup of the closed set is bounded by the limit. Lim inf of the open set is bounded from below by the limit, the G measure of G with respect to the measure. And there's extra condition that F and G have to be bounded away from C. Do you see that? This is exactly the same as the Portmanteau theorem in weak convergence, except that you have extra condition that these sets have to be bounded away from C. So if C is an empty set, this is exactly the weak convergence. But with non-empty C, this is a generalization of the weak. So the key theorem is that this measure of our interest. So we want to prove the LDP of this. This measure normalized by this number converges in M to this C measure. So just look at this. This means that for any F, this is bounded. Lim sup is bounded by this. So this is exactly the same form that I've shown here. And it resembles the large deviation, classical large deviation. So the only difference between here and this here. Oh, so the difference between these two is that I have specified what K matters, which K that matters. But other than that, it's the same. So once you have this, then this is corollary. And so how we prove this? Exactly through the asymptotic equivalences. So we say that two random elements, sequence of random elements in S, they are asymptotically equivalent if the distance, the probability that the distance is bounded from below, distance stays. So the two of them stay far from each other below, far from each other by delta. Also, and if you normalize it by epsilon n, if that goes to 0, then we say that they are asymptotically equivalent. And the asymptotic equivalence is with respect to epsilon n. So this notion is useful because if xn and yn are asymptotically equivalent, then this and also we know that if we know that one of them converges in M, then we know that the other one also converges to the same limit in M. So if we have asymptotic equivalence between x and yn, and we have M convergence for one of these, so the limit theorem of this kind for one of these, then you get the same limit theorem for the other one. So remember that we had these objects, this one, this one, this one, and this one. The simplest to the most complex, but they are all asymptotically equivalent. So we prove LDP for this, we get LDP for this. And this, if you look at this one is fundamentally finite dimensional, right? Because this is a step function with j jumps. So if you decide the jump points, if you decide the jump sizes, then this is completely characterized. So this is LDP for this is basically finite dimensional LDP, although this is sample path LDP. Okay, so I thought I would have at least one proof here, but let me just skip it because there are lots of other things that okay, so all right, so this is what I have discussed so far summarizes how we obtain the LDP for the Lepie process with one-sided additives. But if you have different regular variation in the positive part and negative part, then story becomes slightly more involved. And these machineries that I'm going to talk about becomes very useful. So suppose that you have two M convergent. So mu n1 converges to mu1, mu n2 converges to mu n2, mu2 in M S1 C1 and M S2 C2. Then the product also converges to the product of the limit. But what's the space? It's in this form. So you see that here, suppose that C1 is this, and this is S1 minus C. So x-axis is S1, y-axis is S2. This is C2, and this is the rest of S. Then what you're taking away is these. So it's hard to tell between green and yellow. This is what you take out, and so this is what you're left with. So going back to the definition of the M convergence, you see that this holds for all sets, all Fs that are bounded away from C. So if you have smaller C, then there are more sets, right? So if it is bounded away from C, it makes C smaller, then it should still be bounded away from C. And there will be more sets that are bounded away from the smaller C, but it's not compared to the original C. So M convergence is you get more useful bounds if you have smaller C, smaller set C. Here, you do get some nice combination of so that nice result about the product, but this set is a little bit too big. By the way, this is I've stated this in terms of two sets, but it's actually general. You can actually make the image the product, and the statement becomes changes for okay, again, the proof I wanted to mention a little bit, but let me skip it because there might be opportunity to talk about this tomorrow because I'm gonna talk about the uniform version of M convergence, and the Portmanteau theorem doesn't matter there. But anyway, let me move on. So the next theorem, though, so you have this M converges in this space. The next theorem allows you to make this set C smaller. How to you can come up with smaller C by combining multiple M convergences. So we are almost running out of time. So let me not elaborate this. But the point here is that if you have you can combine multiple M convergences and make this set C smaller. So with these two machineries, you can actually prove that two Levy processes, the product of jointly, they have this M convergence, where this set you subtract is this set. So this is again a set of product of the non-decreasing step functions, but the index the index of the union is over this set. So L1 and L2, for which L1 plus L2 weighted by alpha minus 1 and alpha 2 minus 1 is less than particular J1 and J2, which are these two. So if you think of this as cost of jump in the first process, cost of the jump in the second process, then this is how much you have to pay if you make L1 jump in the first coordinate and L2 jump in the second coordinate. And this is the same cost associated with J1 and J2 jumps. So these are indices that have less cost or less than equal to cost compared to J1 and J2. So these are pair of step functions that have less cost than J1 and J2, less than cost J1 and however, J1 and J2 satisfy this, but you subtract that. You exclude that. So why is this helpful? Because the two-sided Levy process, if your Levy process has both upward and downward jumps, and they have different regular variation, then you can decompose it into the ones with positive jumps. So we're going to call this plus and this minus. Then we have M convergence of these two. And one useful machinery in light field counterpart was Hunter's principle. There is something that corresponds to that in so this is basically continuous mapping or contraction principle for M convergence. And so yeah, let me just I'm not going to read this thing, but the point is that if you have continuous function and but in N convergence you need a little bit more. So the inverse image should be bounded away for any bounded away set. So that's the extra condition, and this is satisfied if the function is Lipschitz, for example, but it doesn't have to be Lipschitz. Anyway, if you have this thing or that with the same property holding almost surely, then you have continuous mapping principle for the M convergence. So we know we have M convergence for this, and this function is continuous mapping. In fact, Lipschitz. So therefore, the subtraction of these two, which is x and bar, the original two-sided related process, does satisfy M convergence, particular C. So this is a statement. Now you have two arguments, J and K, so number of upward and downward jumps. And this argument, this minimum is basically, so what is this? This was the cost here. So this is equal to alpha 1 minus 1 J plus alpha 2 minus 1. Okay. So you minimize the cost over the step functions with J jump that intersect with A. So for a step function, you add J and K jumps, upward and downward jumps, and you pay this much with each upward jump, and pay this much with each downward jump. The minimum cost is the argument minimum of that cost is R, J, and K. So the same large deviation. So this is a lower bound and this is upper bound. This measure is specific form. So very similar to one-sided case, but just natural extension and one side. Okay, so that's how we can handle multiple different regular indices of the regular variations. Let me just finish with mentioning that. So why did we come up with this? Because classical large deviation principle does not hold for J1 topology or for Levy processes. So we have counterexample that applies to any two-sided Levy processes. So it's not like there are Levy processes for which the classical large deviation principle doesn't hold. It's more like for J1 topology, no Levy processes satisfy classical LDP. So this is fundamentally fundamental limitation of the classical framework. So this framework seems to be indeed the right one for regular variables.
Is it possible to change the topology?
Yes, if you change if you weaken the
M1
topology,
also.
you do have
So like, if you use M1, like what do we lose then?
if you use M1, so for example, in M1 topology, allows
But this is for two-sided or one-sided, like, sorry.
right. So one side is much more clear. In one side you can make M1 topology work out. Two-sided, not sure.
Hmm.
But anyway, yeah. So M1, what M1 topologies allow is to approximate this with these things, and so again, M1 is coarser than J1, so you have less useful bound. So yeah, right. So you don't get as useful bound as J1, but
But you get bounds, fine.
right. So you get some bounds. But by the way, you don't have to. That's not the only way to proceed. You can actually weaken LDP framework itself. So in J1, so what we can do is actually this what we have proved the sample path large deviation that actually implies the so-called weak large division principle. In other words, the upper bound holds for compact sets, not all the closed sets, but it does hold for compact sets. It's not great, but you do get some bounds, and also you can extend. You can consider extended large division principle, which sounds like stronger version of large division, but it's not. It's actually weaker version of large division principle. So extended LDP does hold for J1 topology or lattices. And yeah, I should cover just this. So there, the Prof and Mogilsky actually does have classical large deviations, but extended large deviations. The log asymptotics with extended large deviations for J1 topology. But it's log asymptotic, so it's not precise. And it's extended LDP, so the bound is not as useful. So yeah, what we have here is slack asymptotics or J1 topology. Okay, thank you.
I'll just say a comment about the M convergence. So I think it's fair to say that Sid Resnick has been one of the key proponents of that theory. And with Philip Linscock and Chang-Han Rhee, I think they have a big paper, and Sid is now he's working on a book.
Yeah.
It's hopefully going to be published later this year.
Right. Yeah, I probably should have made it more clear. It's M1. The theory of M1 convergence was one of the key components of our proof, and Sid Resnick and Linscock. They are the originators. But these machineries that I told you.
So he actually has the same, almost this picture. He has it. I saw a book manuscript.
This
He
one.
has like pictures like that as well. Yeah.
Yeah. So
Even the same colors. No, just
yeah. These are from
Not the same theorem, I hope.
the same thing with the same colors. Yeah.
All right. Yeah. Thank you.